All right, hello. So this is the first problem of Unit 1 exemplars, problem 3. This problem is we're starting with the more general relationship for intensity that we talked about in class, deriving the classical intensity of blackbody radiation, or the Rayleigh-Jeans law. So first we're starting with the general intensity, where I as a function of v and t is equal to 8 pi v squared over c cubed over epsilon, where I is intensity, v is frequency, t is temperature, c is the speed of light, and epsilon is the average energy of the modes. So we need to figure out how to sustain the average energy of all the modes, or using the sustaining waves. From the classical energy spectrum, we can look at the continuous energy spectrum, and we want to first solve for the epsilon. And this is equal to the fraction of the integral from 0 to infinity of epsilon e to the negative epsilon over kt d epsilon over the integral of e to infinity, 0 to infinity, to the negative epsilon kt d epsilon. So we need to figure out how to integrate this. We're going to start with the denominator because it's easier. So we go here, integral kt is a constant, so that's a value that we can take out eventually. We're going to do a u substitution to make things easier. So we're going to set u equal to epsilon over kt. So now we've done our u substitution, we can plug things back in. So we have kt working through the integral, we have our u substitution, we solve the integral of e to the negative u, and then we plug u back in, take it from 0 to infinity, we find that that's 0 minus 1, so then negative kt becomes kt, and that will be our value on the numerator. So now we want to go and solve the numerator, now that we found the denominator. It's very similar, except that now we have it times pretty much the same integral, except it's times epsilon inside of the integral. kt remains a constant. We're going to set same u substitution, where d epsilon equals kt du. So that lets us go to 0 to infinity and this ukt is equal to epsilon using this. So this is a hard integral to solve. So we're going to say that it's similar to another integral that we talked about in class that is much easier to solve. Where it goes 0 to infinity x e to the negative alpha x dx equals partial derivative in terms of alpha of 0 to infinity e to the negative alpha x dx. From there, we can go partial derivative of e to the negative alpha x over alpha equals e to the negative alpha x partial derivative of negative alpha x partial x equals negative x e to the negative alpha x. Using this form, we can take this, say that it's equal to kt squared times the integral of u e to the negative u du equals kt squared 0 minus 1, using this same 0 minus 1 that we found from the denominator, since it's essentially the same integral. So that leaves us with just kt squared. We can plug it back into that equation for epsilon, get kt squared over kt, so then you're just left with kt. Plugging that back into the final equation for intensity, we have I as a function of Vt equals 8 pi v squared over c cubed kt. And that's our final equation. Now, this is a reasonable result because the intensity is dependent on temperature, which has been determined experimentally. So that's kind of just something that we know. And then the next part of the problem, we want to discuss why this relationship results in the ultraviolet catastrophe and describe and outline the approach that Planck used to find Planck's black body radiation law. So, now that we have solved out all of this, we want to look at the ultraviolet catastrophe. And this is viewed best graphically, where we're looking at I as a function of the frequency compared to the frequency. And when we use the equation we just derived, it basically just goes up parabolically. And this is for a constant, continuous single temperature. And this is showing that the higher the frequency light that's emitted, the intensity will be higher. This just goes parabolically up though, which isn't realistic, which is why this is considered a disaster, because this is basically approaching infinity. So instead, what Planck did, he took the same idea, same graph, except his looks like this. So the reason why Planck's peaks and then goes down is he saw the ultraviolet catastrophe and figured that the continuous energy spectrum was not the way to go about graphing this intensity with blackbody radiation. He realized that using the discrete energy spectrum instead of the continuous and creating an equation or a sum for the intensity, there becomes a certain frequency at each temperature that results in a peak intensity, which would be like right here, some T, some frequency. Therefore, solving/avoiding the issues surrounding the ultraviolet catastrophe where it just continues to go up. And this provides a better way to measure the intensity with blackbody radiation. And so that's kind of how he was able to solve it and fix it. So thank you.